Okay, good morning. After a long weekend, it's time to get started again. So as usual, we're going to start with the reading quiz. So please close your notes for a moment. And after the quiz, I'm going to say a few words about the exam. But right now, we're going to start with the reading quiz. So. Okay, that's the first question here. Okay, I'm going to close this in a few seconds. 5, 4, 3, 2, 1, and 0. And correct answer, of course, is B. Okay. Closing in a few seconds. 5, 4, 3, 2, 1, and 0. And correct answer again is B. Okay, closing in a few seconds. 5, 4, 3, 2, 1, and 0. And correct answer is C. And one more. closing in a few seconds. 5, 4, 3, 2, 1, and 0. And the correct answer here is E. Okay, very good. Okay. As promised, just a couple of words about the exam. So overall, as you can see from the histogram as well, I mean, the performance was excellent. I mean, the mean was 80%. And I looked through, also through the combined scores with the first midterm exam. And there was actually a few people who did better on the first midterm than on the second. So overall, the scores are actually even higher than that. So that really shows that you prepared well for the exam. There was I'm going to go through two questions, and those were the two questions that had the lowest percentage correct. They both had only about 50% correct. And I just want to make sure that everyone is on board with the answers. So the first one of those two was the one on the muscle spindles, and just remember that this is supposed to be a negative feedback loop. So if it starts out, the stretch of the spindle results in increased action potential generation. So if it's a negative feedback loop, the outcome needs to be that the action potential generation is actually decreased. So if you know that the spindle, the stretch generates more action potentials, and that it's a negative feedback loop, I mean, those two facts alone should essentially guide you to the answer, because this here, the correct answer here is C. So it generates more action potentials, which results in activation of the alpha motor neurons, which relaxes the spindle and decreases the firing rate of the sensory neuron. And I think the wrong answers here were somewhat distributed over the different possibilities. So that was the first one that caused the most trouble, and then this one here was the second one that caused the most trouble. And actually, the correct answer here is A, because the parasympathetic nervous system constricts the pupil, and most people who get it incorrect just put the opposite answer. So the sympathetic nervous system actually does exactly the opposite, which is dilation of the pupil. And the rest, I mean, the reason why none of these other answers can be correct is because there's the transmitters or the neurons actually don't match up. Okay, so those were the two questions that caused the most trouble. So on almost all of the other questions, they were at least in the 80% range are correct. Okay, so just take a look at these two topics, because these are also topics that will be on the finals, on the final again. But like I said, overall, I hope you're happy, reasonably happy with your score. But I'm quite happy with the overall performance of the class. Okay. Okay, so with that, any other questions about the exam? Okay, if there's no questions, then we'll go back to where we left off, and we'll talk about a bit more about the physics of flow, of blood flow, of course, and then we'll talk about the heart, and in particular about the generation of pressure by the heart, and then about the regulation of heart rate and contractility. And if we get that far, we'll talk a bit more about electrical conduction in the heart muscle. So just as a reminder, the pressure that the heart produces is, of course, pressure that pushes blood through blood vessels and is called blood pressure. And as with any physical process, nothing moves unless there's a force, in this case, the pressure, and the pathway, which in our case is the blood vessels. And if this is the case, then Ohm's law, or a version of Ohm's law, applies. And we call the blood pressure P and the resistance R. And the flow that emerges is proportional, directly proportional to the pressure, and inversely proportional to the resistance. So the more resistance, the less flow. And then also keep in mind that and I already mentioned this, what you mostly need to be concerned with is the delta P. So the decrease in pressure between one end of the blood vessel and the other end of the blood vessel. So that delta P in this case would be 20 millimeters HT. So, and that difference drives the flow down the pressure gradient. Okay, and then we started talking about the key factor that contributes to resistance, which is the radius of the blood vessel. And I'm going to tell you a fairly complicated formula, but you really only need to know some key elements of it. And fluid flow in general, is governed by a law that's called Poiseuille's law. French. So Poiseuille's law, and I'm just going to put the whole version of it. So it's pi multiplied by r to the fourth. So r is the radius. And then the pressure in minus the pressure out. And that's divided by 8. And then a term that's called eta, and L for length. Okay. And you can actually take this apart. So this term here, P in versus P out minus P out, corresponds to the pressure. And then the remaining elements in the equation, they correspond to 1 over r, okay? And so if you flip these around, then r would be, so r is now the resistance, would be 8 multiplied by the length multiplied by eta divided by pi and divided by r to the fourth. This r here is the radius again. So don't mix up the two different r's. This r is here, the resistance. Okay, so what useful things can we learn from this formula? So the resistance is directly proportional to the length, okay? So in this case, that would be the length of the blood vessels. And I already mentioned, the length of the blood vessels doesn't change, in at least not in the short term, okay? So this is actually, the length is a constant in the cardiovascular system of the body. This term, eta, is the viscosity. So, and blood is actually pretty thick, it's pretty viscous, okay? But the viscosity of the blood also, on average, does not change. So it remains equally thick. So we can also consider that a constant. Can anyone think of a situation when the viscosity of the blood might be changing? Yes?
Fluid replacement or dehydration.
True.
Sorry.
But what?
Fluid replacement or through dehydration?
Yeah, so if you really change if you put a lot of extra fluid in your blood, then the amount of red blood cells and white blood cells would be relatively low, and that would change the viscosity. So another example, if athletes perform blood doping, they increase their red blood cell count, and that actually increases the viscosity of blood. And that can be, as you know, it can be quite dangerous because all this, in the end, has effects on your blood pressure and on the heart. Okay, so but then the key factor that changes on a relatively short scale in the cardiovascular system is the radius of blood vessels. And we already talked about the fact, that blood vessels are actually innervated in many cases. So by the sympathetic nervous system, which releases norepinephrine, which changes the diameter of the blood vessel. Okay, so that constricts blood vessels. Okay, so that can be changed on a relatively short scale. So when we talk about changes in blood pressure, we have to take the radius of the blood vessels into account. Okay, and because the relationship here is inversely proportional to the fourth power of the radius, that implies that when you decrease the radius of a blood vessel by a factor of 2, so decreasing by a factor of 2 means it's now 1/2. If the radius is 1/2, then radius to the power of 4 will be 1/16. So that means the resistance will increase. So if the radius is 1/2, the resistance will increase by a factor of 16. And the inverse is, of course, also true. If you double the radius, the resistance will decrease by a factor of 16. And keep in mind that radius and resistance are inverse of each other, as you can see in this formula here. The radius here is on the bottom of this ratio. So in other words, R and that's also the main message of the slide up there. So the key to remember here is that relatively small changes in the diameter of the blood vessels can result in very large changes of the resistance. Okay, so how does resistance and pressure change over the course of the cardiovascular system? So this is what's shown here, and you can already see here that On this vertical axis here, you have blood pressure, and on the horizontal axis, you have the different types of blood vessels. And the pressure, the heart generates the pressure. So the pressure is, of course, highest at the exit of the heart, which is in the aorta. And you can see that this here, if you read this value, it's probably around 95 millimeters Hg. And this is what we call the mean arterial pressure. And you also find this abbreviated with MAP. So that stands for mean arterial pressure. And that value is about 95. So, and it's the mean because you probably know that an ideal blood pressure is 80 over 120, which means the minimum 120 over 80. Okay. So, and this is approximately the mean of these values. And I'll get to the fact in just a moment why your blood pressure actually is measured as two different values. And but let's take a look at this now. So the pressure, of course, highest in the beginning, and then it gradually drops all the way to the end. Okay, and it has to be that way because in every section, the pressure in the beginning has to be higher than the pressure at the end, so that the flow of blood is in one direction, okay? So you can see that the pressure at the beginning of the capillaries is always higher than the pressure at the end of the capillaries. So that means the blood flows from the arterial side to the venous side. And then you can also see that the pressure difference, the steepness of this curve here, is not equal along the entire extent. So this is not a straight line, but you can see that the largest drop here is in the arterioles, and that's also where the pressure gradient is the highest, okay? So and I told you last time that the flow needs to be constant in every section of the cardiovascular system. So, and flow, which is established, is pressure divided by resistance. So if, let's just say the flow is 100 to plug in an easy value, okay? So if the pressure is 80, then the resistance would need to be 0.8 in order to give you a value of 100, okay? So if you increase the pressure, let's say you increase the pressure to 100, you would need to divide by 1 to give you the same value. So that means if you want to keep flow constant, if you have higher pressure, you also need to have higher resistance, okay? So, and you can see that the maximum pressure difference here is in the arterioles. That means that the maximum resistance is also in the arterioles. And I mentioned this because this is where the majority of the regulation of blood pressure occurs, is by changing the diameter of the arterioles. And I just mentioned changing the diameter changes the resistance really substantially. And this is really the key regulatory element here. And then also, I told you the pressure is really high at the exit of the heart. Here on the other side, this is where the blood returns to the heart. And you can see that at this point, we're very close to zero. We're not quite at zero, so there's still enough pressure to guarantee some flow of blood into the heart. But at that point, the pressure has dropped substantially. And then the last parameter that we need to consider is the velocity of flow. And this, I hope this is not too counterintuitive, but the velocity of flow is inversely proportional to the cross-sectional area. So, so velocity is Q divided by the area. And that means that if blood vessels are very narrow, and that means that the blood needs to flow faster in the narrow section than it needs to be in a very broad section. So if you've ever had the pleasure of watching a creek or a river, they actually increase their speed of flow in narrow sections, okay? And that's because the water that arrives at the narrow section all needs to go through the narrow section. And in order for that, for the same amount of flow to go through a broad section and a narrow section, it needs to speed up in the narrow section, okay? So if you would apply that to traffic, for example, so if a highway is 2 lanes instead of 4 lanes, okay, the cars would need to drive twice as fast on the 2-lane section, which of course no one is doing, okay? So you get a traffic jam, okay? But in order to get the same number of cars through the 2-lane section, you would need to drive twice as fast in the 2-lane section, okay? So, so if there is a more narrow pathway, the flow needs to be faster to get the same amount of fluid through. Okay, so let's go through some of these key parameters of the circulatory system. And I'm going to open this up for the first round, and then you're welcome to discuss and okay, just to clarify here, so we are talking I told you that the circulatory loop, of course, branches into many branches, and then they all come back into just a couple of veins, okay? So what we are trying to estimate now is the flow and the pressure through the entire cross-section. So all of the blood vessels at any level are combined, okay? Not just a single blood vessel. Okay, so with that, I'm just going to collect the answers, and then you can discuss for a moment. So I'm going to close this in a few seconds. 5, 4, 3, 2, 1, and 0. Okay, so go ahead, discuss, and then we'll take a second round. that's why I can't get through to anyone, okay? Okay, so while we are collecting the last few answers here, perhaps you could let me know which answer you think is correct. So, yes? Yes?
I think it's B because P Q is flow, Q equal to V times A, and V times A is constant.
Yes, so the flow is constant. So how about the pressure? So pressure is not constant. So where is pressure high and where is it low? So it's high on the arterial side and low on the venous side, okay? So how about velocity? So why do you think that velocity is not constant? Yes?
Because flow is constant and cross-section area is not.
So the cross-sectional area is not constant, okay? So where do you think where do we have the largest cross-sectional area in the circulatory system? The velocity is not necessarily related to the pressure difference, actually. Yeah, where's the largest cross-sectional area? Yeah, not necessarily. So you're thinking that the pressure difference needs to be large when the cross-sectional area is.
No, I'm saying the cross-sectional area needs to be larger than the pressure difference is large.
The cross-sectional area needs to be large for the.
Where the pressure is large, you need a smaller, you need a larger resistance, right?
Yes, but.
You're going to need a smaller cross-sectional area.
Yeah, I see where you're going with that. So you could solve that through the resistance, but it's a little more complicated than that because there's actually there's local regulation of pressure difference. So, and it's correct. It's adjusted to so. It's a little more complicated than that because there's two factors going into it. One is the pressure difference, and the one is the relative cross-sectional area compared to other compartments. So yes, you could solve it through looking at those two factors. Okay. So, but the major cross-sectional area is.
I didn't see the aorta.
So yeah, the aorta is the place where a single blood vessel has the largest cross-sectional area. But when we talk about cross-sectional area, we also need to consider all the sum because the blood flows in parallel through all these other blood vessels. For example, the blood flows through all the capillaries at once, not just through a single capillaries. So we need to take the total cross-sectional area into account. Yes? Yeah, so the highest total cross-sectional areas is the capillaries. They are very thin individually, but you have so many of them that in some, they make the largest cross-sectional area. And because the largest cross-sectional area is, okay, I'm going to close this. The largest cross-sectional area is in the capillaries, which also means that the velocity of flow is the slowest in that section of the body. Okay, so as you can see here in this figure, total cross-sectional area is largest in the capillary, and it's relatively small in the aorta and in the vena cava because these blood vessels are individually very large, but there's only one or two of them, okay? One aorta, two vena cava, okay? So, and then the velocity is inversely related. And as someone pointed out correctly, you can see that there's some small, mismatches here, and that results from the fact that the pressure difference is also not linear, along the entire system. Okay, so with that background on blood flow, we'll now go talk about the organ, that generates the pressure in the system, and that's of course the heart. And the heart acts as a pump, and the pump pushes blood into the aorta and into the arteries, and there's two phases of the cardiac cycle when it pumps. There's a phase when it contracts, and then there's a phase when the muscle relaxes, okay? And we call the phase where the muscle contracts the systole, and the phase where the muscle relaxes the diastole. And I already mentioned to you that the atrium and the ventricle don't contract at exactly the same time. Okay, it's actually the ventricle contracts first, and then it pushes blood in. The atrium, of course, contracts first. It pushes blood into the ventricle, and then when the ventricle has filled, the ventricle contracts. Okay, and we call the atrial contraction the atrial systole, and the ventricular contraction the ventricular systole. So as you can see here in this figure first, the ventricle fills first, pushes blood in. Did I say again? The atrium fills first, pushes blood into the ventricle, and once the blood is in the ventricle contracts and pushes blood into the aorta, if you're talking about the left side of the heart. Okay, and then of course after the contraction, the relaxation follows. And take a look at the time axis here, okay? So I already mentioned, if your heart beats at 60 beats per minute, that's 1 beat per second. So that means 1 beat is 1 second long, okay? And the atrial systole takes up a very short fraction of that. So about 1/10, about 100 milliseconds. The ventricular systole takes up about 250 milliseconds or so. And then the remainder is the phase when the muscle relaxes. Okay. And now we can look at a couple of features of this process, and there's two different volumes that we usually refer to. And what's shown here in this graph is the volume of blood that's in the left ventricle at any given time, okay? So, and you can see that the minimum here is around 65 milliliters, okay? So that means the ventricle is never completely empty. There's always a remaining amount of blood in it. So even at the end of contraction, there's still a remaining amount of blood in it. And we call that remaining amount of blood at the end of the contraction, the end systolic volume. And you can see from the figure up there, it's about 65 milliliters. So now, before the ventricle contracts, it's fully filled, and full filling of the ventricle corresponds to a volume of about 135 milliliters. And the filling, of course, occurs during the relaxation, okay? So, the ventricle is maximally filled at the end of relaxation. So we call the maximum volume, therefore, the end diastolic volume. And that's about 135 milliliters, okay? And then the difference between these two values is if I calculate correctly, 70 milliliters in this case, okay? And that difference we call the stroke volume. And that's the volume that's ejected from the ventricle at every stroke. Okay, if that's 135 milliliters in the heart at the beginning of the contraction and 65 at the end of the contraction, the difference between the two is ejected from the heart. Yes?
So is atrial diastole occurring during ventricular systole?
Is atrial diastole? Yes. So the atrial diastole is occurring whenever there's no atrial systole. So during this entire 900 milliseconds, the atrium would be in diastole. Yes.
Do all four chambers of the heart have the same stroke volume?
Yes. They do, because they have to, otherwise, but we don't call it stroke volume for the atrium. But the same amount, I don't even know. So the same amount of blood needs to, of course, flow through the atrium on every cycle, because otherwise it wouldn't end up in the ventricle, okay? And then if 70 milliliters are ejected from the left heart, you also need to eject 70 milliliters from the right heart, otherwise blood would accumulate in one of the two loops, okay? So, okay, so then there's one more important feature, of course. I told you already about the heart valves and the fact, that they prevent a backflow. Actually, let me skip this and go right here. So the heart valves prevent backflow, okay? And you can see here that during ventricular contraction, the mitral, and we're talking about the left side of the heart now. During ventricular contraction, the mitral valve is closed, and the semilunar valve is open. So that means the blood can't go back into the atrium, but it's pushed out only into the aorta, okay, in that configuration. During the ventricular diastole, the opposite is the case. Now the mitral valve is open and the semilunar valve is closed, which means during this phase, the blood can fill the ventricle. It can come from the atrium to the ventricle. Okay, so just remember, and should be pretty straightforward that when the heart ejects blood, the semilunar valve needs to be open towards the aorta. When the ventricle fills, the mitral valve needs to be open so the blood can flow from the atrium to the ventricle. So now we are going to look at the generation of pressure by the heart. And I already mentioned, that on the aortic side, the blood pressure is usually high. On the venous side, it's usually low, okay? And you can see that here. So aortic pressure here is starts at around 90, drops down to a minimum of about 80. And then when the ventricle contracts, it is pushed up to 120 and then slowly drops again during the ventricular diastole. Okay? So, and this is why we have two measures for the blood pressure. So one, the 120, is the maximum value that you achieve during the ventricular systole, and 80 is the minimum value that you achieve just before the onset of the ventricular systole. Okay, so that's the diastolic pressure is the lower one, and the higher one is the systolic pressure, because that's achieved during the systole. Okay, so, and then you can also see here that the pressure inside, so let's go to the venous side. Okay, so here is the atrial pressure, and you can see that atrial pressure is always relatively low. But you can see that the pressure inside the heart actually flip-flops between these two values. So the line in red now is the ventricular pressure. And during the diastole, it's very low. And then once the heart muscle starts contracting, the pressure becomes very high. And during the relaxation of the heart, it drops down again. Okay? And if we now put our information on the heart valves on top of this diagram, you can, of course, see that when the blood flows from the ventricle to the aorta, that's when the semilunar valve is open. Okay? So during this phase here, when the blood is pushed into the aorta, the semilunar valve is open. Okay? And one fact that's important here is with that valve open, the aorta and the ventricle essentially become one continuous chamber. Okay, so you have the ventricle and then the aorta, and if the valve is open, then this becomes a continuous chamber. So if something is a continuous chamber, that means the pressure in the two parts needs to be about approximately the same, okay? So you can actually see that when the valve is open during this phase here, that the pressure in the two chambers is approximately the same, okay? And you can also see the same during the diastole when the heart is relaxed. So now the mitral valve is open. So this is the atrium, the ventricle. Now the semilunar valve is actually closed. The mitral valve is open. And now the atrium and the ventricle become one continuous chamber, okay? And during that phase, when the two are a continuous chamber, you can see that the pressure in the two parts of the heart is approximately the same, okay? So it's impossible, you know, if you have an opening between two compartments, it's impossible to have different pressures in the two compartments, okay? So having the same pressure is an indication, you know, that the valve is open. So now, if you look carefully, there's of course something interesting occurring in between these phases when the pressure is equal with one or the other compartment. And there's a phase when the pressure inside the ventricle increases from the atrial level to the aortic level, okay? And how do you think the pressure inside the ventricle can differ during this phase from from both of the compartments. So what happens here during this phase when the pressure of the ventricle differs from both the atrium as well as the aorta? Yes? Okay, so the AV valve is closed. How about the semilunar valve? So AV valve is the mitral valve in this case, okay? So in this case, so now this is an interesting phase because when the heart muscle starts contracting, so both valves become shut, okay? So this is diastole. So the ventricle is still relaxed, okay? Once the ventricle starts contracting, first thing that happens is the mitral valve closes, okay? So now the valve closes, but there's no blood going out this end yet, okay? So why is there no blood going out this end? Because in order for blood to go out, you need to have at least the same pressure as the aorta, okay? So you have a phase, where both valves are closed, okay? So now when both valves are closed, blood can obviously not enter or leave the ventricle, okay? It's shut on both sides. So the volume inside the ventricle is constant. The chamber is shut, okay? Nothing can get in or out, so the volume needs to be constant during this phase. And the pressure rises, okay? And we call this phase the isovolumic contraction. Okay, so iso means there's no change in volume during this phase, okay? So you have a phase where the ventricle starts contracting, but it needs to build up pressure until it reaches the aortic pressure, okay? And during this entire phase, both of the valves are shut. And then when it reaches the aortic pressure, okay, when the pressure here is approximately equal to the pressure, when the pressure in the ventricle is approximately equal to the pressure in the aorta, the semilunar valve will open, and that's when the ejection of blood is starting. So what happens during this phase when the pressure of the ventricle goes down, independent of the two compartments that it's connected to? So during the ejection, the semilunar valve is open, okay? Of course, because the blood needs to go into the aorta. So what happens here when the pressure of the ventricle falls below the pressure of the aorta? So now you get, when this pressure in the aorta is higher than in the ventricle, that means you get a little bit of backflow. And that small amount of backflow pushes on the valve, okay? And it closes the valve, okay? So now you have a situation where, but the pressure inside the ventricle is still relatively high, so that also still pushes on the mitral valve. So you have another phase, when both valves are closed, okay? So you have an isovolumic relaxation here, okay? So again, both valves are closed. So the volume inside the chamber does not change, okay? So what is the volume inside the chamber at this point? What is it? So how much volume do we have inside the chamber? Yes? it's 65, okay? So here, in this, during the relaxation, remember, we just pushed as much blood as possible into the aorta, okay? So at this point, there's only 65 millimeters left. So those remaining 65 milliliters remain the same along the entire way down, okay? Because now both valves are closed, the volume cannot change, so you need to have 65 during this phase here, okay? During this phase, so we have the end diastolic volume that's reached here, okay? And then during the entire isovolumic contraction, the end diastolic volume, which is 135, will be inside the ventricle, okay? So during this phase, when the pressure rises, we have 135 in there. During this second phase here, when the pressure falls, we have 65 remaining, okay? And now we can put the change in pressure and the change in volume into one figure, okay? So in this graph here, time is on the horizontal axis, okay? But now I'm going to show you a graph that has pressure and volume on the two axes of the graph, okay? And this is the version with time. This is the version with volume and pressure, okay? And you can put together what we just talked about. So we have this phase here where both valves are shut, okay? This end diastolic volume is reached at point B here. And so end diastolic volume is 135 if you look over here. And now the pressure rises while the volume does not change. So that's shown here. 135 in the ventricle, pressure rises, okay? Now at this point, the aortic semilunar valve opens, okay? So now pressure still keeps rising somewhat, but at the same time, we are pumping blood into the aorta, okay? Because we are pumping blood into the aorta, that means the volume of blood in the ventricle, of course, decreases, okay? So that's shown here until D. So that's when we have reached the end systolic volume, which is 65. And now the aortic valve shuts, okay? And now the end systolic volume, which is 65, is inside the ventricle while we drop down to a really low pressure, okay? And then the mitral valve opens, and then once the mitral valve opens, the ventricle can be refilled. So the volume increases again until we get to point B again, okay? So keep in mind that there's these phases, you know, when both valves are shut, okay? So stroke volume. So now let me get back to a picture that I skipped before. So stroke volume is not constant, okay? So, of course, you know, when you exercise, you know, you pump more blood through your circulation. That means stroke volume needs to go up, okay? So, so that's an active process, but there's also a passive part of that, okay? So if there's more blood returning to the heart, you also want to increase your blood, your stroke volume, so the blood doesn't back up, you know, on the venous side, okay? So if there's more blood returning, you also need to increase stroke volume. So, and there's a passive process that is called the Frank-Sterling law that, and as in this process, what happens is that when the heart gets passively stretched by incoming blood, okay, when there's more incoming blood, the strength of the contraction actually increases, okay? So this is a self-regulatory mechanism. If there's more incoming blood, strength of the contraction increases, which means more blood gets ejected, okay? So that makes sure that nothing gets backed up. And we call that the Frank-Sterling law. And then I told you there's also an active mechanism to increase stroke volume, and that is achieved through epinephrine, okay? So the sympathetic nervous system can actually increase the strength of the contraction of the heart. So you probably have all learned, that that the sympathetic nervous system, epinephrine and norepinephrine, increase heart rate, okay? Of course, it increases heart rate, but along with an increase in heart rate, you also get an increase in the strength of connection, okay, of contraction. So epinephrine also and norepinephrine also increase the strength of contraction. So if there's more strength of contraction, more blood gets ejected, okay? And you can see that these two processes can combine, and they can result in even more increase of stroke volume, okay? So in the first line here, you see the normal process. So you have a normal end-diastolic volume, normal contractility, and you have a normal stroke volume. So if you have an increase in contractility by the sympathetic nervous system, you can increase stroke volume because you now eject more blood. If there's more blood returning, the Frank-Starling law causes an increase in contractility, so you eject more blood. And then in the last line here, the two processes combine. So you have more blood returning, more blood being ejected, which results in a large increase in stroke volume. So just think about it this way. If you fill the ventricle with more blood will come out. If you contract it more forcefully, more blood will come out. Those are the two mechanisms, that can result in an increase in stroke volume. And I should say here, that stroke volume, heart rate times stroke volume, is determines the amount of flow that you get, okay? So let's just go through an example. If you pump 70 milliliters at a heart rate of 60 beats per minute, you have a flow of, 4,200 milliliters per minute, if I calculate this correctly, okay? Makes sense? If let's say you go to a heart rate of 100 per minute, not that fast, okay? And let's say you eject 100 milliliters, you have a stroke volume of 100 milliliters. You can increase this to 10,000 milliliters per minute, which, by the way, are 10 liters, of course, okay? This is 4.2 liters, okay? So these two factors combine, to give you the total amount of blood that flows through the circulation at any given time. Okay, so we already talked about stroke volume. We already talked about the pressure. So now we're actually going to talk about this side of the equation here, the heart rate, okay? And this is an important piece of motivation for what I'm going to tell you, okay? So so usually, I just showed you this graph here. The contraction of the ventricle takes about 250 milliseconds or so, okay? And then, so that's the ventricular systole, okay? And the remainder of the cardiac cycle was the ventricular diastole, when the ventricle was relaxed for about 700 milliseconds, okay? So now, if you increase your heart rate and you keep the length of the ventricular systole constant, that would mean that at some point, you would use so when you increase your heart rate, that also means your cardiac cycle gets shorter, okay? So if you go from 60 beats per second, which is you have 1 second for one beat, but if you go to 120 beats per second, that means you only have half a second for one beat, okay? If you keep, the time it takes to contract the ventricle constant, if it remains at 250 milliseconds, that means you're already using now half of the cardiac cycle for the contraction. So you have less time for the relaxation, okay? If you go to 180 beats per second, that means now you only have a third of a second, for each cardiac cycle, okay? So if you still keep your contraction at 250 milliseconds, okay, you have essentially no time, for relaxation anymore. So, and remember, during the relaxation of the ventricle, that's the time when the blood fills back into the ventricle, okay? So you need to have time for the blood to come back to the ventricle, okay? So in order to leave enough time for the filling, okay, you need to shorten your contraction, okay? And that's exactly what happens, as you increase your heart rate, the time it takes for the heart to contract shortens, okay? So rather than it taking 250 milliseconds, it only takes 150 milliseconds for the contraction, okay? And we call this effect the inotropic effect of the heart, okay? So, and the bottom line is, this shortening of the contraction and increasing the strength of the contraction, which we call the inotropic effect, needs to go hand in hand with an acceleration of the heart rate, okay? And an acceleration of the heart rate we call the chronotropic effect. And then there's a third effect that comes into play, which we call dromotropic, which is the speed of the conduction of the signal across the muscle of the heart also needs to increase, okay? So remember, I told you about the conducting system that takes starts at the sinoatrial node, okay? So, and that needs to eventually, end up at the ventricular, so that signal needs to end up at the ventricular muscle, so that conduction speed also increases. So, so these three effects go hand in hand. So when we talk about an increase in heart rate, that means at the same time we also increase the conduction speed and we increase the strength of contraction and decrease the time of contraction, okay? Okay, and now in the last few minutes, I'm going to talk about the ionic mechanism that leads to that actually leads to both the inotropic effect as well as the chronotropic effect. So let's talk about the acceleration of the heart rate first, okay? So acceleration of the heart is done by the sympathetic nervous system, okay? And the source of the transmitter here can either be norepinephrine or epinephrine, okay? So epinephrine comes from the vagus nerve, not the vagus nerve. Epinephrine comes from a postganglionic cell, okay? Norepinephrine comes from a postganglionic cell. Epinephrine, of course, comes from the adrenal medulla, okay? It's a hormone, okay? But both of these transmitters and hormone act on a receptor on the heart that's the beta-1 receptor. So that's one of the adrenergic receptors. And that receptor is equally sensitive to norepinephrine and epinephrine, okay? So in the end, it doesn't matter what the source is of the molecular signal, whether it's neuronal or hormonal, okay? So they both act on the receptor, and the receptor is equally sensitive to both. So, and then we already learned that one of the consequences of activating a beta-1 receptor is an increase in, so this is now inside the cardiac cells. So the beta-1 receptor is, of course, on the, in the membrane of the cardiac cells, okay? So, that results in an increase in cyclic AMP inside the cell. So that's the second messenger in this case. And these beta receptors are on both. So they're on the autorhythmic cells, and they're also on the contractile cells. So on all the different cell types. So orthorhythmic, remember, is the same as, we call those also non-contractile, or we call those pacemaker cells. So those are just different names for the same type of cells, okay? So, but remember, they're in the autorhythmic cells and in the contractile cells, okay? So both have beta-1 receptors. So in these cells now, the increase in CAMP results in a decrease open time of potassium channels and an increase in calcium influx. And now in the autorhythmic cells, okay, because these cells actually also have remember, these are the cells that have the HCN channels. And I want to remind you that HCN stands for hyperpolarization activated cyclic nucleotide gated channel, okay? Cyclic nucleotide gated, okay? So now this actually comes into play, okay? So the CAMP that's generated by this signaling mechanism here actually will activate the HCN channels, and of course only in the autorhythmic cells, because those channels don't exist in the contractile cells, okay? So in the autorhythmic cells, you have 3 mechanisms. In the contractile cells, you have these 2 mechanisms, okay? So now so this is more or less a direct effect of CAMP. So now this effect here, the increasing calcium influx emerges because the CAMP actually phosphorylates calcium channels. And I will pick up here on Thursday, okay? I think it's the end of our lecture time for today. Okay, I'll see you on Thursday.